So, good morning. I'd like to welcome you to the ML Workshop 2024. We have two talks for this first session. If we can welcome Guillaume Munch-Maccagnoni, who's going to talk on designing interrupts for ML and OCaml, looking for a sound design for asynchronous exceptions. Thank you, Guillaume.
Hello, everyone. The topic of this talk, that's what happens when you press Ctrl-C on your keyboard because you're fed up with what the program is doing. Oh, thank you very much. Okay, so you press Ctrl-C, and your program has to react to it. And most often, you want it to continue. You interrupt what you were doing, but you want the program to keep being responsive after that. So that's a classic problem. When we are talking about ML, we are talking about programs that may contain state, so local and global state. What happens if you interrupt and your data structure becomes in an invalid state? So a while ago, upon rumors hearing that OCaml developers wanted to remove asynchronous exceptions from the language, or at least make them more marginal, so I surveyed the use of asynchronous exceptions or interrupts in the OCaml ecosystem. So I came up with a list of packages that depended on this feature. And there are quite many uses of that. There are some high-profile programs in there, programs written by impressive people. And what you find is that tools like proof assistance, compiler, interactive language tools, or CLIs, they do rely on this feature. And what they do is they want to react to signals like SIGINT or SIGAlarm, SIGTERM, or even SIGPipe. I saw that. They want to check regularly if some memory limit has been reached and interrupt the program if it's too high. What they want to do with it is they want to put a specific message for what happened upon this interruption, or they want a specific user interaction, or they even program a distinct behavior, distinguishing what happens upon a voluntary interrupt and a crash, and we take a different course of action. And in the OCaml world, you can even have errors that arise from your finalizers. I'm not saying that it's a good thing, but it's the situation, and we want to work towards making the situation a bit saner. So there are further motivations, which is to go towards having a notion of cancellation in the asynchronous, green thread frameworks. This corresponds to the idea that when you move your scheduler into your program and you write your own scheduler, then you're moving part of the OS into the programming language. So how far do you have to go? Maybe you have to move isolation features from the OS into the programming language. And what's behind this notion of interruption is also a non-defensive model for reacting to errors. So that's related to the philosophy of Erlang, of when you've got an error, the best way to write your program reliably is to fail as quickly as possible, and let the failure percolate to the person who can really react to it. So the point we are making here is that so there is an exception handling model that has been brought forward by the Rust language, which is an evolution of the C++ error handling model. And the claim is that it can be extended to deal with asynchronous exceptions or interrupts. So there are various challenges with interrupts. In ML, they are implemented as exception arising out of thin air. So any code location can raise an exception. It's obviously a challenge for reasoning about stateful program. So when I catch the exception, is the state of my program still in a valid shape? Then when you get into the details, you find issues where maybe before catching my exception, some other exception happened. So now I have multiple exceptions in flight at the same time. So how can we make sense of that? So another challenge is that OCaml has evolved towards systems programming recently. So there's a whole bunch of programs that expect no asynchronous exceptions at all, and that are written with this assumption in mind. Moreover, so the OCaml multi-core project was designed at first around this specific dialect of OCaml. For instance, the notion of fiber in OCaml, there are resources that you need to drop explicitly. So either you use it or you drop it explicitly. You must not let it fall on the ground. So if you have an exception arising in the middle of nowhere, then you don't know what to do. On top of that, we don't want to force programmers to code defensively against exceptions. We don't want to force programmers to apply the program-wide discipline. As we will see, that's a solution that's currently in use to make sense of those interrupts in the ML ecosystem. So, reviewed the current approaches. So, proof assistants like Coq and Isabelle tell you that there are critical exceptions, and you must not catch them. You must let them terminate the exception quickly. So they apply a program-wide discipline that programmers must follow. There's a distinction at runtime between critical exceptions and other exceptions. And when you write a catch-all, you must by hand make sure that your exception is not critical. On to managing state. There are various kinds of state. The first one is the notion of resource. So we take the good advice from Haskell of having a combinator that deals with all the subtleties of the races that can happen between resource acquisition, resource release, and asynchronous exceptions that might happen. And there's a good reference on this topic. Michael Snowman wrote a blog post on this topic. And already here, if you read the blog post, actually you can see behind it something similar to the C++ approach to exception safety. Now, what about non-local state? So something clever in the Coq proof assistant is that there are some stateful computation, but upon an interrupt, it will roll back to the previously known good value. Another thing you can do is to invalidate the state to propagate the information of the failure to other users of the same non-local state. Now, what about if there is some local state? If there is some local state, it will disappear with the part of the program that you're going to interrupt. So it's not an issue in general. And what the Rust programming language came up with is a trait called unwind safe that labels your data structures by telling whether you can recover from an interrupt or not. That means when you are catching an exception in Rust, so you pass your closure to the catching combinator, and the type of this combinator checks that everything inside the closure actually survives this interrupt. So you are forced to explicitly say that you have no local state when you catch an exception. Now, all these approaches, I want to rephrase them, and I want to start from the beginning. It's the difference between the, errors and exceptions. So errors, such as result types or catchable exceptions used for control flow or simply reporting errors that can be handled by the caller. So they must be handled by the caller. And this should be distinguished from the notion of exception, sometimes called serious exceptions, which must be handled only at appropriate isolation boundaries, because it's the role of the person catching the exception to make sure that no invalid state can escape from the part that has just been interrupted. So here, for ML, the term exception is overloaded because if they are catchable and serious exceptions, we want to make the distinction. So Rust has the term panic for that, and it comes with features to ensure isolation. So the distinction, so when we say serious, critical, and all that, we think about a value judgment about what my error is actually. So I don't care about that because I don't know how to program with that in mind. What I need is that I have different facilities in the programming language that are adapted to different ways to structure and reason about the program. And the distinction here is who is responsible for ensuring the consistency of the state. Is it the caller or is it the person who's going to catch the exception? So we can easily outline an approach in ML to make sense of interrupts. This is a bit what happened in the Isabelle proof assistant. You don't have catch-alls. All exceptions are considered as serious. And you need catch-alls to do things like resource management. So instead of doing it by hand, you will be given appropriate language features to do so. So in the end, you get a model where when you program, you don't have to think about whether there is an asynchronous exception that might arise or not. This is not your concern. It's the concern of the person who's going to catch this asynchronous exception. So when you write a task, it has to be written like any program. All you have to do is to fail fast in the event of a failure. And you have to use the provided resource management features to manage your resources. But the catcher must make sure not to share state, its personalized state with the task, unless the state is protected. And once you take this approach, and when it's done right, then there is no possible interrupt happening between raising an interrupt and handling this interrupt. This means that we also get rid of the problem of having multiple exceptions in flight. So when you get into the details of an established language like OCaml with specific constraints like backwards compatibility, it becomes a bit more complicated. So I guess I'll go quickly over those slides. There are lots of details, so maybe I don't have the time to explain it all. We have a list of requirements for having interrupts in OCaml and making the situation better. The first one is that interrupts need to remain opt-in for backwards compatibility reasons. There are some asynchronous events that we don't want to delay, for instance, related to memory profiling. And we want to make it impossible to confuse catchable and serious exceptions. For instance, we don't want someone to be able to raise not found in the middle of nowhere. We want to make it possible to enable certain code transformation for optimization purposes. So we want to get rid of the hypothesis baked inside the compilers that every allocation points may raise an exception. So the proposal is to add a new kind of exception besides the exceptions that currently exist, that are distinct from other OCaml exceptions, and that are not caught by catch-all handlers. We don't provide a catch-all for those exceptions. Instead, we provide the suitable resource management features. Another part of the proposal is that we want to distinguish asynchronous events depending on whether they are raising or non-raising. That means that there are some asynchronous events that are run promptly but cannot raise an interrupt, and some that can be delayed, but then that are allowed to raise an interrupt. And with more constraints come more guarantee. It actually becomes useful to have this notion of non-raising callbacks because it guarantees you that you are on the exact fiber that provoked this asynchronous event. So there are various details to make things right, and there are things that are that become a bit complicated and require a bit of work. First, what happens with system calls that may receive EINTAR? And what happens with standard library globals? Are they interrupt safe yet? So this has to be audited and fixed. And there are reflections about backwards compatibility. So to conclude, some work has been done, like implementing a notion of masking to delay asynchronous events so that I don't have interrupts in the middle of paths where I don't expect them, for instance, resource management, so that we can implement some resource management combinators. So there was a prototype of that written 5 years ago, and that needs to be updated. There's work done to see how it could be to not have asynchronous exceptions in f-lambda2, and that not only enables code optimizations that would not be possible before, but it's actually required for correctness of the f-lambda2 compiler. And so our work with Leo White and Stephen Dolan is to reconcile all these different trends and different ways of using the OCaml language. So as a perspective in OCaml, we want exceptions to either become panics or checked exceptions. So we want there to be an evolution path towards a saner use of exceptions. of course, for backwards compatibility reasons, the currently notion of exception might remain for a long time. And finally, what this illustrates, this whole talk, is that structured programming is an ongoing research paradigm. That means I have features that sometimes do not let me express what I want to reason about. So that's the case for go-tos that were replaced with more structured facilities. And when you think about exceptions, it's a bit the same. So what am I really doing when I am programming with exceptions? So I'm not using the whole facility. I'm using some well-designed, some parts of it in a well-designed way that lets me reason about it. So, and we want to put that structure directly into the language. And finally, when studying that, we found this unwind safe trait in Rust that lets you say whether you can survive an interrupt or not. That has some kind of model character that I invite the community to study because it looks quite interesting. Thank you.
Thank you, Guillaume. We have time for some questions. If people would like to come up to the microphone, forgiving is probably easiest at the front. If there are any questions. In which case, I have a question. You said the prototype implementation is roughly 5 years old, so presumably that predates multicore or camel, therefore. Is there anything that you've looked into in terms of interrupts specifically, so things like Control-C handling, for whether there's an elegant way of doing that using effects? Whether there's a way of doing that using an effect instead of asynchronous exceptions. So effectively to allow a domain to unexpectedly perform an asynchronous effect, but that might allow resumption of it. Is that something that's been looked at?
So the question is, can I do something more than raise an exception during the asynchronous events, and can I perform effects? So that's related to a notion of asynchronous effects that has been studied by, oh yes, Dolan, yeah. And Mathieu Preta. Thank you. So they have this notion, presumably, you could extend all that not just to asynchronous exceptions, but asynchronous effects that would be performed inside the asynchronous callbacks. So there's a lot of hurdles to implement that in OCaml for very low-level questions. Mainly, so there are two questions. First, it's currently implemented in C. So you'd have to capture the C stack, which is something that the OCaml compiler does not know how to do. And it's not just a technical problem. It's, if you think what happens if you're currently in some interoperability between C and OCaml and you have a callback from OCaml to C, you have the same issue. What happens if your asynchronous effects just happens while you are inside your callback, while you are in C? And so there are challenges. So maybe it's desirable, but it's a lot of work.
So, kind of connected to that question, have you thought about handling incoming asynchronous effects in JavaScript? So imagine running your application in a web browser. Does that change anything? I mean, will this work in WASM JS of OCaml?
So I'm not familiar with the way those are implemented in JS of OCaml, to be honest. The outline we gave are on the language side, but I expect to be dirty details when you look under the hood.
So I'm sort of specifically thinking, I don't know, if I just get some sort of signal, I press a button or something. Should I see that as a kind of panic or something else? Or does that require some more general notion of asynchronous effect?
Well, it depends what you want your button to do. If it's a button that needs to interrupt what you're doing, then you need something like that to hook your JavaScript event into some kind of asynchronous signal. So here, we just want to handle the way you can interrupt your stuff. We are not looking to do anything more fancy. So maybe
I guess closing your browser window, would that just turn into some other kind of panic?
I'm sorry, can you repeat?
If you have a web application, you close the window.
Mm-hmm.
Is that more analogous to the kind of thing you?
Yeah, that's very analogous to the applications that that use SIG term. Yeah.
Thank you. Thank you. I think if we can thank Guillaume one more time.